Okay, I think there is not much on integral domain. So a commutative ring with unity that has no zero divisors is what we call an integral domain. Okay, before I move down to idempotent, I think I have a question we can all put our hands on under zero divisors. So let's try this. X squared plus 3x minus 4 in Z12. X squared plus 3x minus 4 in Z12. So you show me the zero divisors in this particular example or classwork exercise that I gave you. So you can follow this same process, and you can also do it in such a way that you have a tabular form. So you have something like this. You have x, that is your value of x's. This is in Z12. That's from 0 to 11. So 0 to 11. Then the set you are working with, that is x squared plus 3x minus 4 in Z12. So then you can now start putting these zeros inside and give answers in a tabular form, just like what we have here. So instead of you working it out like this now, I don't want to solve this because it's an exercise for you. So if you put 0 here, you give me what the answer is. After you might have divided it by 12, except if the answer you are getting is not up to 12, so you can just write back. So for example, let me just say pick 2. That's 2 raised to the power 2, that's 4. That's 6, that's 10 minus, okay, this should be 6. Let's try 5. 25 plus 15, that's 40 minus 4, that's 36. So 36 divided by 12, you pick the remainder and then put it here. Then you have answers here in tabular form. Then you can now look at the ones that is giving you zeros at this right hand side. You check the value of x's that are giving you 0 here. So the value of x's that are giving you 0 here are the zero divisors. So this is another way to also do it in case you are given. So now this now takes us to the next one, which is the idempotent element and also the nilpotent element. So let me just clean. Now, okay, idempotent element. So first of all, we need to first understand the definition of all of these things. So all of these things we are saying are inside rings. So we have ring as a whole. Then inside rings, we have zero divisors inside a ring. We have integral domains inside a ring. We have idempotent elements inside a ring. We have nilpotent elements inside a ring. We have associates inside of them. So how are we going to know that this element inside a ring is an integral domain, is a zero divisor, is an idempotent element? Is basically what all of these things is saying. Just like all of these are just subsets inside a ring. So the first thing I'll define is an idempotent element. So let's just say an element. Let's say an element, I used A the last time. Okay, let me say X. An element X of ring R is said to be idempotent is said to be an idempotent element if x squared equals to A. That is what x squared equals to x. That is what I mean is that x times x gives me x. In the real sense, I don't think this is possible, but abstract algebra says it's possible. Okay, so fine. Let's pick examples. I think I have some examples here. How to find an idempotent element. So let me start from smaller ones. I have a smaller one here. Okay, let me start from, let's say, Z13. But before I give this, I have some key information you guys have to put down under idempotent element. So this information, when you get a particular idempotent element, the one you've gotten gives you an idea what the next idempotent element will be. That's what the key information is here is all about. So one, if let's say X is an idempotent element, then 1 minus A is also an idempotent element. 2, the number of idempotent elements in Zn equals to 2 raised to power d, where d is equals to number of prime divisor of n. Okay, I think these are the two basic informations you have to put down. Okay, let's start with this. I'll start with the smaller one. So let's say we were told to, an example, find the idempotent element in Z6. Find the idempotent element in Z6. So if I'm to first write out the residues of Z6, that would be from 0, 1, 2, 3, 4, 5. Now looking at this definition, so an element X of ring R is said to be idempotent if X squared is equals to X. That is, if I pick an element and I multiply it by itself, it gives me itself back. Okay. So if I'm to pick these elements one by one, 0 squared equals to 0. If I multiply 0 twice, it gives me 0. And that's equivalent to 0 mod 6. So 0 is an idempotent element because it satisfies this. 0 is always an idempotent element. It is always an idempotent element of any given integer domain. So 0 is always. So you can see that multiplying by itself gives me 0. Let's try 1 raised to power 2. This will be 1 mod 6. I can't divide 1 by 6 because 1 is not up to 6. So 2 raised to power 2 will give me 4. That's 4 mod 6. 3 raised to power 2 will give me 9. 9 in mod 6. 9 in mod 6, that's 9 divided by 6. How many 6 will I say in 9? 1 remainder 3. So 3, that's 3. 3 mod 6. So you can see that 3 squared is equivalent to what? 3. So 3 is there. Let me tick. This is not there. This is not there. This is there. That's what this is saying. So 3 squared equals to 9. 9 in mod 6 will be 3. If I pick 4, this is 16. 6 in 16. 2 mod, 16, 6, that's 12, and then that 4. Okay, that's 4 mod 6. Okay, yeah. 4 is also part. 5. 25. 25 in 6. 6 in 25, 4. And that one, that's 1 mod 6, which is not. So from what we have here, we've seen that 0 So 1 is there. 0, 1, 3, and 4. So therefore 0, 1, 3, 4 are idempotent elements in Z6. So I think I was saying something the other time that x squared equals to x is not feasible in the real sense, but I think I saw something x squared can be equals to x if x is equals to 1. So okay. Now, like I gave you these two rules, because the next one I'm going to give you now is Z30. So does it mean that I have to like list out all the residues in Z30, start doing all of this before I now know what the idempotent element is now? So these two key informations really work. So it's saying that once we get an idempotent element, 1 minus that idempotent element is also an idempotent. So what they are trying to say is that, for example, let me just take an example now. We've seen that 3 is an idempotent element. 1 minus this 3 will give me minus 2. By the time I do this minus 2, okay, it's a mistake. X, yes, thank you. So if 3 is an idempotent element, 1 minus that idempotent element, whatever I get is also an idempotent element. So we can just check it. So I don't know. What should I claim? Let me just manage my body. I think I still have space. So the first issue you have now is to first find the idempotent element in Z30. That's the first thing we have. And I know that if I'm to write out my residue, this will be from 0 to 29. So if I try out, so it means that 0, so I've said 0 is always an idempotent element. That is not a big deal. 0 is an idempotent element. 1 is an idempotent element. Let's start. 2 raised to power 2 will give me 4. 4 raised to power 2, that's 4. And this will be equivalent to 4 mod 30. So it's not returning, but it's supposed to return back 2 for me. So 2 is not. 3 will be 9. That's 9 mod 30. 4 will be 16. 16 in mod 30. 5 will be 25. That's 25 mod 30. So 6. That's 36. 36 in 30. That will be 1 remainder 6. So I'm picking my remainder. That's 6 mod 30. So you can see that x squared is equals to x definition here. So 6 is there. Now once I get this, we already know. Just know that 0, 1 are always idempotent elements. So once I get this 6, then this comes into play. Now it says that if x is an idempotent element, that is, if 6 is an idempotent element, 1 minus 6, that's minus 5, is an idempotent element. How? Minus 5 raised to power 2 will give me 25, and this is not up to mod 30. Okay. Alright. So minus 5 mod 30. Okay, not 5. Minus 5 mod 30 is minus 1 times 30 plus 25. So minus 1 times 30 is minus 30. Minus 30 plus 25 will give me minus 5. So this is how we do negative numbers under modular arithmetic. So minus 30 plus 25. So that means this will be 25. So we normally pick this here. So let's take, for example, you are giving minus 6 mod, let's say mod 15. How do you solve this? Since this is negative, this will be, you start with the modulo you are giving, minus 1 times 15. Then you look for something you can add to this to give you this. That's 9. So my final answer will be 9 9 mod 15. So that's basically what I was doing here. So 25. So this 25 here is an idempotent element. 25 raised to power 2, I think that should be 6 to 5. 6 to 5 in 30, that's 30 remainder 25. So 25 mod 30. So 25 is an idempotent element. So I think I've gotten 0, 1, 6, 25. Now, take note, you can't be doing 1 minus x all the time because I said 6 is the idempotent element. 1 minus 6 gave us this. We need to continue again from 7 to know the next idempotent element. Then you will do this to know the one that follows, just like what I've done. So you cannot say you've gotten 6, then you apply this, you got 25, then you still want to apply 1 minus 25. No, that's not what this is saying. So once we know the next one, then I can apply. When you apply, you continue again, you know the next one, then you apply this one. So if I try 7, okay, 7, that's 49. Let me clean. I'll just be writing my so if I try 7, that will be 49. 7 squared, that's 49. 49 in mod 30 is I think 19. 8, 64. 64 in mod 30 is 4. 4 mod 30, and just place on that. Mod 30. 9 is 81. 81 in mod 30, that's 2. No, sorry. Yes, 60. 30 times 2 is 60. That's 21. 10. 100. 100 in mod 30 is 10. So 10 is there. Now I've gotten the next one. 10. Now, since I've gotten the next one, then I'll now come and apply this rule number 1. 1 minus 10, that's minus 9 in mod 30. So when I do the mathematics here, minus 9 mod 30, that's minus 30 times 1 plus 21. So 21 will be the next one. You don't need to say, okay, if you just want to, 21 raised to power 2, what should I give me? 441. So 441 in mod 30 is 21 mod 30. So 21 is part. Now you continue again. You stopped at 10. You continue from 11. So you don't do, that's basically what I'm saying. You don't do 1 minus 21. You look for the next idempotent element before you can use this rule. So that's how it keeps on going. 11, 12, 13, 14, 15 will be the next one. So let me just list it out since you know how to do it. 15 and then 16. Now another question I think some of us would have been asking ourselves in our brain is, how do we know how many idempotent elements exist in a particular domain? So if I'm giving Z100, fine, this rule number 1 has given me an hint on what the next idempotent element will be. But when do I know that this element that I'm giving, this particular question I'm giving, this is the total number of idempotent elements in it? That is where this comes in. So in any integer domain you are given, this Zn. So for example, the first one, Z6. The number of prime divisor of this 6 tells you the number of idempotent elements in this Z6 and what are prime divisor. So when they say prime divisor, that is elements that can, prime numbers. So from the word, first of all, divisor, I think we took 0 divisors and we said that so the number of prime divisors, that's Zn equals to 2 raised to power d, where d is the number of prime divisor. Okay. Now if I pick 6, a prime divisor, 1, is 1 a prime number? I don't think so. 2, 3, yeah, just 2 and 3. are the prime divisors of 6. That is, numbers that can divide 6, numbers that are prime that can divide 6. That's what they are saying. Obviously, 1 will divide 6, 6 will divide 6, but 1 and 6 are not prime, so we cannot pick it. So 2 and 3, which is how many? This is 2. 1, 2. So when I place it here, that's 2 raised to power 2, and this gives me what? 4. So this 4 tells me that I'm going to have 4 prime divisors in C6, and if you count it, we have 1, 2, 3, 4. So I know the number. So Z30 also, if I try to do Z30, I list out the prime divisors of Z30, 2, 3, 5, 0, 1, 6, 25, 10, 21, 15, 16. So 2, 3, 5. Okay, I think it's just 3. Rest are not prime divisor. So let's put it here. That's this 3. 1, 2, 3. So 2 raised to power 3 give me 8. So it basically tells me that the number of prime divisors in Z30 is 8. And if I'm to count it, 1, 2, 3, 4, 5, 6, 7, 8. So these two key informations are very key. So first of all, if you are giving a test or whatever, classwork or whatever, you can basically know the number of prime divisors you have. Even before you start, you already know that, okay, this is what you are working towards to. So when you are solving and you are writing your final answers, and maybe it is lesser than what you have calculated, or is more, you know, you can trace back your mistakes and all of that. So before I go to nilpotent, let's look at it again. An element X of ring R is said to be idempotent if this property is satisfied. So these are the two key informations that I have given you, and this is how to calculate if an element is an idempotent element in a particular integer domain. So I think I can clean. So we are moving to nilpotent elements. Okay. So nilpotent element. So the word nil should have given us an idea of what this is trying to say. So let R be a ring, and A should be a member of this set R. It's a ring. So anywhere you see R in abstract algebra, it's a ring with no real number. So this A in R is called a nilpotent element, n dot e, if A raised to power n equals to 0, where n is some positive integer. So remember that idempotent is x squared. If it's x you are using, that's x squared equals to x. So nilpotent is saying let R be a ring and an element A is a member of this ring. So I can only say this A is a nilpotent element if it satisfies this particular property, where this n is some positive integer. Now, same way, I also give some particular hints on some idempotent elements that will help us in, first of all, knowing the idempotent element and the number of idempotent elements we are going to have. I think we also have the same thing in nilpotent elements, so I'll try as much as possible to give before we start. So I think let me just write keynotes. So if, take note, if R is is number 1. If the ring we are looking at is an integral, is an idempotent, is an integral domain, sorry. So I think I've given what an integral domain is. An integral domain is a commutative ring with unity that has no zero divisors. That's an integral domain. So if R is an integral domain, then R does not possess any non-zero nilpotent element. That's number 1. I think number 2. Okay, these are all on integral domain. Okay. Let's just move on. So let's take, for example, Z4. We are asked to look for the nilpotent elements 1, 0, 1, 0, 1, 2, 3. Now we need to take note. I think that was what I was trying to say. So we mark ZP. You can just write this somewhere. We mark so I gave Z4. Now if you look at 4, this is very key. So if you look at 4, 4 is not a prime number. So anytime you are giving an integer domain like this, and you are checking domain you are giving, which is 4, if it's not prime, then it possesses no nilpotent element. Same thing if I give like let's say Z6. So Z4, you have 0, 1, 2, 3. So I'm going to be testing all of this one by one using this. So I have, okay, let me first try it with 4. 4, so I need to look for the prime factor of 4 that I can multiply together to give me 4, and that's 2 times 2. So 2 times 2 will give me 4. So there's also a formula for this to know the number of nilpotent element that I have. It is also 2 raised to power d also. But the d here is quite different. So first thing first, you look at whatever you have for, write out, there's a table. Let's assume we're giving, let's say 6. So 2 will go in 6, 3 times remainder 1. 3 will go in 3, 1 remainder, and this 2 times 3. So you are giving me the prime factors of 6. So 2 times 3 will give me 6. Obviously, there are other numbers that can give me 6, but we are only picking those that are prime. So now, I have 2 prime numbers here. So that basically means that this will be P all over the prime numbers that you have, which is 2. So P is 4. That is the P I have here. This is what I'm trying to say. ZP. To know the number of nilpotent elements you have, it is this P all over, how will I write it? The prime factors of this P. So whatever you use to divide this P, whatever it gives you here is the number of nilpotent elements you have. So you have, and that is 4 divided by 2, which is 2. So it means you are going to be having 2 nilpotent elements in Z4. If you do the same thing in Z6, so that's, if I'm to write out, I think I've done it, so that's, so 6 all over 2 times 3. That will be 6 all over 6, and that will be 1. Which means that in Z6, I'm only going to be having 1 nilpotent element in Z6. It cannot exceed 1. This cannot exceed 2. If I'm giving, let's say, Z12, so I express this 12 in terms of prime numbers as a factor of prime number. Okay. 2, 6, 2, 3, remainder 0, remainder 0, 3, 1, remainder 0. So this is 2 times 2 times 3. So I have 2 twice, so you are not picking, if a number occurs twice, you are only picking it just once. So this will just be 2 times 3. So that will be 12 all over 2 times 3. That's 12 all over 6. 6 divided by 12 is 2. So this tells you that there are 2 nilpotent elements in Z12. So take note of what I said there. When you're having to just pick one, take it to other and put it here. So this formula here that we are using tells us the number of nilpotent elements we are going to have. So it cannot exceed 2 for Z12, cannot exceed 2 for Z6, cannot exceed 1 for Z6, 2 for Z4. Now let's solve, since we know that already. Now under integral domain, let's just cast our mind back under integral domain. Now if we are given any integer domain, let's say Zn, if this n is a prime number, if the n you are given is a prime number, it has no ID, it has no integral domain. So you can just say, okay, find integral domains in Z7. So integral domains means that a commutative ring with unity that has no zero divisor. I think we talked about zero divisor. We said that this 7 or this element in Z7 can be a zero divisor if there exists another element such that when we multiply together it gives 0. So if you check your definition, whereby the first element, that's A, and the second element B, both of them are not equals to 0. But when I multiply them together, they are giving me 0. So this is now saying that if P is prime, there is no integral domain. And what is integral domain? A commutative ring with unity that has no zero divisors. Which means that there are non-zero elements there are non-zero elements. Instead of this one now to be not equals to 0 and this B not equals to, because basically what they are saying is that, let me make this clear. So if they are saying ZP, where P is prime, has no integral domain, has no integral domain. First thing first is we need to first ask ourselves is, what is an integral domain? Integral domain is a commutative ring with unity that has no zero divisors. What's a zero divisor? A, B or B, A equals to 0, where A and B are not equals to 0. So if P is prime and they are telling me that is an integral domain, it means it will not have a zero divisor. So anytime I have zero divisors, so it will have no zero divisor. So anytime I have zero divisors, then it means that it is not an integral domain. So basically, if I'm to say it has no zero divisors, it means that one out of these two is equals to 0, or the both of them is equals to 0. Because if you are saying it has no zero divisor, it means it's not satisfying this rule. That's what this means. So if you are giving an integral domain, an integer like this, to look for the integral domain, you check this P. If P is prime, it possesses no integral domain. So I just wanted us to just know that. So now, how do you find the nilpotent element? I've shown us the numbers of nilpotent elements that can exist in whatever domain you are given. I've given you the formula. I gave also for idempotent elements. So it basically tells you that you don't exceed. Once you just get 2 for 12 now, if you just get 2, you know you are stopping there. There is no nilpotent element that exists in Z12 again. So let's start with the Z4 that I give. Residues of Z4 is 0, 1, 2, 0, 1, 2, 3. So if I'm to start, pick 0. So because they said here, they said n, where n is some positive integer. So positive integer 1, 2, 3, on and on like that. So 0 raised to power 1, you give me 0. 0 raised to power 2, you give me 0. So for any positive integer n, this will continue to give me 0. And that's basically what he's saying. That when you pick this A, for this to be a nilpotent, it must satisfy this. So I'm picking 0 now. I'm raising it to any positive integers, and it's still giving me back 0. So 0 is a nilpotent. I think we said 2. So 4, that's 2 times 2. That's 4 divided by 2. That will be 2. So we have 2 nilpotent. So we need to find the second one. Let's pick 1. Let's take the second one. 1. 1 raised to power 1 will give me 1. Power 2, 1. Power 3, 1. So 1. 1 is a nilpotent element here. Let's pick 2. Oh, it's not equal to 0. Thank you. I was still thinking of idempotent element. So 1 is not. Let's pick 2. 2 raised to power 2 will be 4. That's 1 mod. Okay. 2 raised to power 2. That's 1 mod 3. 2 raised to power 3. Okay. Okay. 2 raised to power 2 is 4. So I'm working in mode 4. 2 raised to power 2 is 4. 4 in mode 4 is 0. 2 raised to power 3 is 8. 8 in mode 4 is 0. 2 raised to power 4 is 16. 16 in mode 4 is 0. So if I keep on raising this thing to some positive integers of n, I find out that I'm getting 0. So it basically follows that rule. A raised to power n equals to 0, where n is some positive integer. So my nilpotent elements in Z4 are 0 and 2. It doesn't go beyond this, since you've already seen that there exists only just 2 there. So that's basically what we have. So let's try another one. Two raised to power 1 is 2. Basically, this 2 is not, we are working in Z4. So we are working in Z4. Okay, let me just say. That's another angle to look at. But basically, I know from here that if I'm to look at all the residues here, which is 4 residues I have here, I've seen that I can only have 2. I've seen 0, 1 cannot, 3 cannot, so 2 can. Then this might be something I might look at. Why 2 raised to power 1 gives me 2, and why they are still picking 2? Because basically, if I'm to pick all other n integers, it's 2 raised to power 5, 6, 7, 8, 9, 10, still gives me 0. Okay. So this solves the nilpotent element. You can try Z12. What are the 2 nilpotent elements in Z12? That's from 0 to 11. 0 will definitely be 1, nah. 2, no. 3, 4. Okay, in Z12, yes, 2. 0 will definitely be 1, no. 2, 3, 4, 5. Let's just try. 6. Okay, let's say 6 raised to the power, that's 36. 6 raised to the power 3. 36 times 6. And 12 divide this. Okay, 6 raised to the power 4. That's 216 times 6. 6, 3, 9, 12. Let's divide it by 12. 6 cancel this how many times? 2 times. 1, 6 times twice. Okay, yes, 6. So 0 and 6. 0 and 6 are the nilpotent elements in Z12. So first thing first, you might have listed so, so you can't just be doing all of these things. So when I say, okay, for example, you're giving Z6, so you wrote out the residue 0, 1, 2, 3, 4, 5. The residues of Z6, and you're asked to look for the nilpotent element in Z6. You can just write solution. Note that nilpotent element in ZP, the number, okay, you can just write the number of nilpotent elements in ZP is given as P all over prime numbers of P. P1 dot P2 dot P3 up until Pk. So you are trying to let your marker know that what you want to do is because you cannot just say, okay, 0 and okay, here it was only 0 we got. 0 is just the nilpotent element in Z6. What happens to 1, 2, 3, 4 without testing it? So basically, if you have written this, it knows that this is the theorem you are following. You have this theorem stuck in your head that the nilpotent element in a particular domain is calculated by this. And you can just say, so if you have 6, you have 2 times 3, you have 2 prime numbers. Using this theorem here, that's 6, 2 times 3 equals to 1. So this one, that means that there exists only one nilpotent element in Z6. Then you can now say, therefore, 0 is the only nilpotent element in Z6. So there's nothing to solve because there's a theorem guiding what you are doing. Same thing in idempotent. So you can also do the same thing instead of you working out everything we've done. I've given you how to find the idempotent and how to know the number of idempotent elements. So you just write down the theorem. Then when you write down the theorem, you can just give answer. So whoever is marking knows that you have a particular theorem you are following. You don't have to do all of these workings. So I don't know if there's still time to take associates. So okay, let me just see if I can give you guys some works to do. So find the idempotent element in, okay, I think I've given you 1 on 0 divisors to do. You can just find the idempotent element in Z10, say Z24. You also look for the nilpotent element in the two of them also. So you can just add this just to do. So you should learn the definitions, what the definitions are, and all of those theorems I am using to back up what I'm doing, my idempotent and nilpotent. It kind of saves you time of solving. But when you are solving, you make sure you are writing the theorem first. So when you write the theorem and you are giving me answer, I know that your answer is based off of what the theorem you've written there. So I think I'll have to take this in our next class because this is a little bit much. So far we've been able to talk about groups, rings, integral domains, zero divisors, idempotent elements, and nilpotent elements. So and I think I've not been able to give examples, like much examples on integral domain. I think I've been able to treat idempotent and nilpotent very well. Zero divisors also, just that it was just one I gave. So basically on zero divisors, it's not just that they just give you quadratic equations. I just give that because that might look maybe a little bit like complex and all of that. But so if you are given, let's say, Z12 and you're asked to look for the zero divisors, you know you are looking for an element in Z12 so that when you multiply, it gives you 0. But note that both elements should be a non-zero element. So nilpotent also, okay. So when I'm coming in the next class, I'm coming to treat more on integral domains, and then I'll just continue off of associate. So all of these things you have said, you keep down those key informations that I've given, and you also pay attention to the definitions that I've given and some of the key informations I've given, especially on rings. When you are asked to define a ring, you are given a particular question and show that this is a ring, you have to define first. Even when you are asked to show what an integral domain, okay, what are the zero divisors, you have to define what a zero divisor is before you now start solving. Same thing goes to the integral domain, and same thing goes to the other ones that I've done. So okay, you can just prepare yourself for more on integral domain, and then we take this in the next class. So this brings us to the end of today's class. So do well to read. Thank you.